In our universe, all things are driven by energy. Energy powers our sun, our environment, our society, even our bodies. Energy is life. New and profound advances in science and engineering are allowing us to harness this energy abundance in marvelous new ways. To create clean, affordable, and reliable energy for all Californians. The SoCalGas Research, Development, and Demonstration Program has enlisted an incredible team of experts in science, engineering, industrial technology, and environmental policy to identify, build, and implement these transformational technologies throughout society. Collaborating with the world's top institutions, we have deployed over $73 million on hundreds of groundbreaking projects over the past 5 years. Hyatt Hydrogen, which could enable transporting hydrogen through existing infrastructure to power fuel cell vehicles and facilities. Doosan Mobility Innovations hydrogen drones that have 4 times the flight capacity of lithium-ion powered alternatives. And hydrogen-powered yard trucks that can move massive shipping loads for 20 hours per day with 0 emissions. These revolutionary projects are saving energy, reducing emissions, and improving air quality, as well as increasing energy safety, reliability, and affordability for all. At SoCalGas RD&D, we believe in clean energy abundance, so we are sharing this pivotal research in order to deploy these innovative technologies across the world. Because energy is life. And we believe a clean energy future will bring a better future to everyone. SoCalGas, Research, Development, and Demonstration. Learn more at www.socalgas.com/RDD.
Hi, everyone. I'm so excited for today's presentation. Good morning and welcome everyone to our SoCalGas RD&D research webinar. My name is Alan Leung and I'm the Customer End Use Application RD&D Program Manager at SoCalGas. For today's webinar, we will be welcoming Daniel Olson with the Colorado State University, or CSU, to learn about their exciting research he performed with the support from SoCalGas RD&D program to explore the impact of hydrogen and natural gas blends on rich burn engines. Just as an FYI, today's webinar will be recorded. You can access today's recordings as well as our past webinar series on our SoCalGas Research and Development webpage. Before we begin, I'd like to walk everyone through the GoToWebinar toolbar that should be visible to all attendees. Please enter any questions in the question box. We'll review them during the Q&A session after the presentation. During the Q&A session, we'll also open up the discussion for verbal questions. Click the raise hand icon to be called on during the Q&A session. Finally, you will find a few valuable documents in the handout box. The SoCalGas RD&D mission is to identify transformative energy solutions, build them, and share them with the world. More information on the program's vision and values are also included on the slide. The RD&D program is divided into 4 areas that span the entire energy supply chain, from low carbon resources, where they look at the renewable gas production, to gas operations focused on technology development of the operation side of the gas supply chain, to ultimately where we use the gaseous fuels from clean generation to customer end use application. I would like to share with you our commitment to the community. we have included with the presentation as an attachment on our equity engagement roadmap. The roadmap shares some of the things we are doing within the community from a research perspective. Finally, I would like to stay connected with our stakeholders in the research community and the general public. Please visit our webpage. You can scan the QR code on the screen, where again, you can find our annual report. You can also find information about our upcoming webinars and news about the RD&D program. Please note that the site is actually under construction right now, so we're expecting some minor changes these next couple of months. And please reach out to the RD&D team via email with questions, comments, or research suggestions. Also, our RD&D LinkedIn webpage with the QR code that will take you there with regularly published posts about our research and research articles. And our RD&D newsletter that comes out periodically, again, with the included QR code on the top right. Now, without further ado, I want to introduce our speaker, Daniel Olson from CSU. Dr. Olson is currently a professor of mechanical engineering at CSU and has been a research scientist at CSU Engines and Energy Conversion Lab for the last 6 years, carrying out various RD&D research on large bore natural gas engines used for natural gas compression. His research group specializes in research and development on industrial engine systems for applications such as power generation and gas compression. I'm excited for Professor Olson to share the results of this research project with our audience. I will go ahead and turn over the controls to you, Professor Olson, so you can get started. Thank you.
Thank you, Alan, and thanks everyone for your attendance. A moment here to share my screen.
You now have control over the presentation, Daniel, so feel free when you're ready to share the presentation. Please take your time. Thank you.
Okay. All right, I'm going to go ahead and get started here. Turn my camera off. So this work was funded by SoCalGas with financial support and in-kind support from Caterpillar, as well as in-kind support from Woodward. The title is Impact of Hydrogen Blending on an 18-liter rich burn natural gas engine with NSCR catalyst. So that is non-selective catalytic reduction. The work really focuses on this particular class of engine and the impact of hydrogen on the performance of the engine and on the emissions. So I'm going to start off with some background information. I'm going to go over this fairly quickly. The main content of the presentation is the engine research results, so I'm going to kind of limit the amount of time that I spend on background. So the work was performed at the CSU Powerhouse Energy Campus. My industrial engine research group has 15 to 20 people, and the bullet points there are a summary of the work that we do. The laboratory is shown at the lower left-hand corner. There, it's the left portion of the building was an old power plant, and the right portion of the building was later added on. The two engines shown at the lower right represent the largest bore, 14-inch bore, 14-inch stroke, and the smallest bore, which would be the CFR engine on the right, automotive size, and then the GMV at the bottom center is a integral compressor engine. We have about 10 engines that are fully instrumented that fall in between those sizes. So hydrogen generation, probably the most popular way to think of this is generating hydrogen from solar and wind, and certainly that is possible in an area that is being researched extensively. So that's one approach, solar and wind being converted to hydrogen through electrolysis or other means. Most hydrogen currently is created from steam reforming of natural gas, but you see there's a wide array of approaches to creating hydrogen. Hydrogen transport is another important topic. The picture at the top right is a tube trailer. When we do hydrogen engine testing at our facility, we order a tube trailer from Air Liquide. It comes in at a little over 3,000 PSI, and we then flow that into the building for testing engines for research purposes. So compressed gas, that's one method for transport. And then another method would be liquid hydrogen at the lower right. The US pipeline network is shown on the left, and certainly that's another viable approach. And there has been a lot of discussion in recent years about blending hydrogen with natural gas in the pipeline network for transport. And that's actually the focus of this research, which is to evaluate the effect on engines, the effect that blended hydrogen with natural gas has on various engines. Hydrogen storage is another important topic. If we generate it somehow, we most likely need to store it and utilize it at another location in another application. Compressed gas is the most prevalent currently. Liquid hydrogen is another important approach, and then there are a number of material-based approaches that are currently being researched. Hydrogen usage, this diagram is conceptual. The current usage of hydrogen is primarily the purple circles at the lower right. The other uses are primarily being researched currently. So back to the natural gas pipeline network. This slide shows more detail on the natural gas pipeline system, and there's some bullet points there on the some metrics and statistics on the U.S. natural gas system. There's about 600 integral compressor engines on the pipeline system. Those are primarily in interstate pipelines, and then around 14,000 smaller gas compression engines. And those engines are used anywhere between the well and the point of use for the natural gas. Here are some examples of gas compression engines. The engine at the upper right is a two-stroke integral compressor engine where the compressor pistons run off the main crankshaft. So all of these engines run on natural gas and compress natural gas. The lower right shows Ajax compressor system, and the lower left shows a gas compression package. The packages at the bottom of the screen would be gathering engines or wellhead engines, so they're closer to the well, as opposed to the upper right picture, which would be on the interstate transmission lines. The engine that would be powering the gas compressor on the lower left would be most likely a 4-stroke rich burn engine or a 4-stroke lean burn engine. So when I get into the results of the research, I'm going to be talking a lot about lambda. And so I'm going to provide a little bit of background on that here. The chemical equation there shows the ideal combustion of a hydrocarbon fuel. So you have just the right amount of oxygen and the right amount of fuel so that you have no oxygen, no fuel left over in the products. And that would be referred to as stoichiometric combustion, ideal stoichiometric combustion. And the air-fuel ratio based on mass is a way to characterize a fuel, and lambda is the ratio of the actual air-fuel ratio to the stoichiometric air-fuel ratio. And if lambda is, and this is a normalized parameter, so the composition of the fuel can change, and this is still a good metric to focus on with regard to engine performance and catalyst performance. So when lambda is lean, that means that there is excess air, and when it is, and it's greater than 1, and when lambda is less than 1, that means the mixture is rich. Other parameters used are air-fuel ratio directly and also equivalence ratio, and those are described on the slide. Natural gas engine emissions, obviously very important, and the focus of engine design and engine retrofits. There's basically 3 categories. Nitrogen oxides are composed of NO and NO2, and those are regulated. They're associated with the high temperatures in the combustion chamber. Carbon monoxide and hydrocarbons are also regulated, and those are associated with incomplete combustion in general, and specifically it is VOCs, volatile organic compounds, that are typically regulated for hydrocarbons. And then on the right are greenhouse gas emissions, and from natural gas engines, we're primarily worried about carbon dioxide and methane. So this slide, getting back to the lambda parameter, this slide shows emissions versus lambda. So lambda's on the x-axis, and then the 3 emissions groups that we've discussed are on the plot on the y-axis. And rich burn engines, also called stoichiometric engines, because it's the equivalence ratio or the lambda value is actually very close to stoichiometric, operate here. And that's actually not a great place to operate for engine out emissions. They're all relatively high, but a 3-way catalyst will be able to function there and reduce all of the emissions to very low levels. Lean burn engines operate in this region where the excess air drives down combustion temperatures and associated NOx, and also drives down carbon monoxide and hydrocarbons due to the excess air for combustion. So hydrogen is normally characterized as volume percent, and this can be a little bit misleading, and so that's why I'm showing this plot. The plot here on the right shows the volume percent of hydrogen, and then the mass percent of hydrogen in this dashed line, and then the energy percent in this solid line. And you can see how 20% by volume hydrogen has a relatively low contribution of mass and energy to the fuel. And so it's a nonlinear relationship, and that's just something to keep in mind as we go forward. Other properties of these fuels are shown on the right. So that is the background information. The next section is on four-stroke rich burn engines, and then the final section will be on our hydrogen blending results. So the engine that we use for this research is a Caterpillar CG137-8 18-liter V8, 400 horsepower, 1800 RPM. This engine is used for gas compression, power generation, water pumping. It is a relatively low power density, about 11 bar BMEP, and a relatively low compression ratio, about 10.25. So it's designed to run on a variety of different fuels, including unprocessed wellhead gas. So the three-way catalyst is a very important part of this system. This is the main emission control device. The engine operates roughly at stoichiometric conditions, so it produces relatively high, large amounts of emissions of NOx, CO, and hydrocarbons. However, those are at just the correct ratio to be reduced across the catalyst. They essentially react with each other and oxygen to form nitrogen and CO2, and that reduces the emissions to very low levels. The catalyst that we used was sized for the California Best Achievable Control Technology requirements, shown there at the lower right. So the requirement for the catalyst to function properly is stoichiometric operation. Roughly, the lambda value actually needs to be controlled very precisely, and we'll see that as we move forward. So that is controlled with the amount of fuel and air feeding the engine. And so we get just the right composition of exhaust products based on the air and fuel mixture to get significant reduction of emissions across the three-way catalyst. So just some more information here about the test setup. We have sampling. We have sampling probes pre and post catalyst shown at the lower right-hand corner there. We use a Fourier transform infrared spectrometer and a 5-gas analyzer bench to measure emissions. So the area of operation with respect to lambda, this region here for stoichiometric or rich burn engines is blown up here. So this is baseline data that was collected, and you see lambda is varied from rich to lean. And on the rich side, the post-catalyst carbon monoxide is high, but then comes down in this region here to very low levels. And then NOx is high on the lean side, and then it comes down to very low levels in the middle. So this is the area of operation right here. And you can see by the lambda values that we need to control the system to a very precise lambda. So a little bit more on that. So this, based on that plot, we can identify a window of operation. So the NOx comes up on the right, and when it crosses the emission limit, we mark that as the limit of the window on the lean side. And then the CO comes up on the rich side, and the limit is 0.6 grams per horsepower hour, and that marks the limit of the window on the lean side. And then we chose our operating point to be right in the middle. And so that's what's programmed into the controller, and that is, what the system is controlled to reduce emissions. On this plot, we see the addition of hydrocarbons, and hydrocarbons are the dashed line, the gray dashed line, and there's really no perfect area of operation. The hydrocarbons are minimized here, but that's really close to this nonlinear portion of the NOx curve. So deciding where to operate is, there's trade-offs involved. Okay, so with that background on the Richburn engine and the baseline data, we'll go into the hydrogen blending results. Our basic hydrogen blending setup is shown here. So we have the natural gas coming into the building and a Coriolis flow meter to quantify the natural gas flow rate. And then the hydrogen coming from the tube trailer goes through a mass flow controller, and we blend those together before the flow goes to the engine. This slide shows some data, some combustion data. On the left-hand side there, you see combustion pressure traces for 0, 15, and 30% hydrogen by volume. We see roughly a 10% increase in peak pressure, and we see the peak pressure location get earlier. The data here on the right shows the ignition delay, which is reduced as hydrogen is added. The peak pressure location gets earlier, the cylinder pressure increases, and the combustion duration is relatively flat. This slide shows fuel consumption and greenhouse gas emissions as hydrogen is blended with the natural gas. So on this plot on the left-hand side, you see natural gas goes down as hydrogen increases. The 20% blend point is something that is kind of a rule of thumb for what various organizations think is possible to blend into the pipeline. So we've focused on that in places in the presentation. The plot at the upper right shows carbon dioxide emissions, and as hydrogen is added, you're displacing natural gas and methane, and so therefore the carbon dioxide emissions come down, since the products of combustion for hydrogen are water and no CO2. The methane emissions are shown at the center, and methane also comes down by about 24% post-catalyst. So this slide shows pre and post-catalyst NOx and CO emissions. Pre-catalyst emissions, we see an increase in NOx. So that's the plot on the left-hand side. That's expected with the combustion peaks getting earlier. And at the same time, carbon monoxide is reduced as hydrogen is added. The catalyst, is going to function somewhat independently of that, and we see relatively flat curves for NOx and CO at the post-catalyst position. So at 20% hydrogen, we went in and did a lambda sweep. And this is kind of the first, negative impact of hydrogen that we saw. If you look at the solid line, that is the 20% hydrogen curve. And so CO comes down, NOx goes up, the NOx curve comes up more to the left. And so that narrows the window of operation by about 28%. So it's still something that is can be dealt with. So it's not a huge deal, but it is kind of a negative effect of hydrogen addition. Another observation that was made was that when the hydrogen was added, there was a spike in lambda. So when we added hydrogen, we added it in 5% steps. So it's unclear how hydrogen would be added in practice if it were being added to the pipeline. So it may be much more of a gradual process, but this is the way we carried out the research. So when we go from 0 to 5% hydrogen, we see this spike in lambda. So the spike in lambda can be explained by the airflow requirement for stoichiometric operation. So here in this table, we have steady state points for various hydrogen levels. And for each of these rows, their steady state and the equivalence ratio or the lambda value is controlled to the ideal lambda value. And at those ideal lambda values, we see the airflow requirement drop. And so if we're sitting here at 0% hydrogen and we step up the hydrogen, the air takes a while to respond. And so at that moment, we have too much air for 5% hydrogen, and the lambda value goes lean. And as a consequence of that, NOx goes up. If you think back to the lambda versus emissions plot, if you go lean, NOx comes up. And so we see the lambda spike here and then the associated NOx spike here. So that's an important thing to be mindful of, and it especially is important when designing controls. Another thing that we discovered was that as hydrogen is increased, it's nonlinear in terms of the amount of air flow required. And so when we transition by 5% hydrogen, if we're starting at a higher value, 25, we actually see a larger NOx spike. Now the controller takes over, and after a few minutes, it's back down to steady state conditions and all the emissions are controlled. The concern comes in if we're having these sorts of spikes, what is the 1 hour average of NOx? What is the 1 hour average of CO? And so on. The CO emissions were basically unaffected because of the behavior is more gradual on the rich side. But for NOx, for some of these transitions, for the way the engine was set up with regard to its controls, we see that a 1 hour average in the time frame of that hydrogen transition, those 1 hour averages are above the limit. But of course, after some period of time, the emissions go down to below the limit. So the final phase of the work, we looked at the controls, and as I mentioned, we received some in-kind support from Woodward, and This engine was actually configured with a Woodward large engine control module, or LECM controls, so that we could do more investigation and research on the controls area. And the LECM basically controls two things. It controls the speed, that's with the throttle valve. So you have a speed sensor feedback, and the speed is controlled with the throttle valve. And then it controls lambda. And so that's controlled with the electronic fuel valve. And the lambda sensors provide feedback for that, which are located in the exhaust. So if we take a look at how both of those control loops respond during one of these transitions, we see that the speed initially drops down and then recovers very quickly. So it's a faster control loop by design. The speed needs to react quickly to load changes, or else the engine could essentially die. The lambda control is slower to respond, and so you see the spike here, and then after a few minutes, it responds and controls back to the set point. So we did some investigation into improving the control. In the controller, we can adjust the PID parameters, the proportional, integral, and derivative control parameters. I'm just going to show some adjustments to the proportional control parameter. So for the 1 hour average, for the 0 to 5% transition, here are some results that we measured. The original control setup is here. If we reduce the proportional gain from 12 to 8, we saw a lower NOx 1 hour average. In other words, the lambda control loop recovered faster. If we go in the other direction, or if we go to 10 or 20, there's a detrimental effect where the NOx 1 hour average is actually above the NOx limit. This value here, or this set of parameters here, is not without trade-offs. The speed control was not as stable, so it's something where if you adjust the speed, the lambda control loop, you may be adversely affecting the speed control loop. So, this is a complex problem, and we just really scratched the surface as far as our investigation of the controls. But the main thing that we're trying to convey here is that when it comes to the hydrogen addition, these transitions, the engine controls can have a significant impact one way or the other. Okay, so that brings me to my conclusion slide. So with regard to hydrogen blending, we went up to 30%. We feel we could have gone higher. That was our target, to go up to 30%. We didn't see any issues with engine operation, no malfunctions of any kind. And this test was set up so that the engine controller basically had no knowledge that the hydrogen spike was coming. So this is really looking at the engine in its stock form and evaluating what the hydrogen blending will do if no action is taken with regard to controls. The post-catalyst NOx and CO did not change significantly as long as the ideal lambda was maintained. The lambda window of operation was narrowed by about 20% with a 20% blend of hydrogen. So that was a negative impact of the hydrogen blending, but it is something that we feel is manageable. With regard to the hydrogen transitions, when hydrogen is increased abruptly, we see that lambda spikes lean, and this causes an increase in post-catalyst NOx. The post-catalyst NOx spike from 0 to 5% was reduced by over 50% by tuning the lambda PID control loop. And then finally, engine operators should be aware that poor PID tuning can result in high NOx production during hydrogen transitions. And again, it's unclear what can be expected in the field as far as these transitions. This is just something that we came up with during the research to evaluate different transitions. The other thing I would say in conclusion here is most of this work is captured in the thesis and a publication led by Nick Katsampis. He was a master's student, and that reference is given in one of the slides above. So if you're interested in learning more, you can get those publications. And that's my last slide. Thank you.
Daniel, thank you so much. Give me a couple seconds while I hop over and change the presentation on my end. Great, thank you. Daniel, again, thank you so much for the presentation. I found it extremely informative. I think these type of engines are one of those areas that are crucial for the energy transition as we decarbonize. And so again, thank you so much. And everyone, thank you so much for attending. And just some house cleaning items. The recording will be available on our website soon. Let me hop on webcam as well, so it's a little bit more personal. And be sure to check out our LinkedIn for an update on when it's ready. You'll be receiving a survey request in your inbox soon. Please take a moment to fill that out. Your feedback will help us improve our webinars and help us select topics that are of interest to you, our stakeholders. And remember, at SoCalGas RD&D, we strive to identify transformative energy solutions, build them, and share them with you and the world. Now, I'd like to open up the webinar now for a 15-minute Q&A and quick reminders about the Q&A session. If you have a question, click the raise hand icon and we will call on you to grant you access to unmute. And then you must manually unmute yourself to ask your question. And then after you ask your question, please kindly go back on mute. And if you'd like to ask questions in writing, please feel free to use the question box. We will ask the question for you. And then it looks like we have the opportunity now for Q&A. So please ask away. And I can start us off because I love the presentation and I was taking notes as we go. So Daniel, my first question for you is, has there been any flashback or any combustion issue, such as hydrogen levels approaching 30%?
Yeah, I think that is a concern. And when we're talking about engines where the fuel and the air are pre-mixed with a carburetor or a mixer, there is a concern about ignition or backfires in the intake system. We did not experience that in our testing up to 30% hydrogen. Certainly, it's for safety concerns, it's a good idea to take a look at that. Things that can be done would include burst diffs in the intake system, pressure relief valves. Those type things can be done, if there's a concern. But for this testing, up to 30% hydrogen, we did not, and for this engine, we did not experience that.
I see. Great. Thank you so much for explaining that. I see actually one of our guests, it looks like Adam Dempsey has raised his hand. So I'll go ahead and call on Adam. Adam, if you can kindly please unmute, I appreciate it.
Can you hear me, Dan?
Yes.
Hey, good presentation, Dan. That was great. I have two really quick questions. You might have shown a plot later on that answered the first one, but you, in the background material, you showed that from a hydrocarbon perspective, the catalyst has a very narrow sweet spot regarding reducing primarily methane emissions. And they can be near zero in that very narrow range. But then even if you step off of that range, is the catalyst reducing unburned hydrocarbons by 30, 40, 50%? Or is it really doing nothing in terms of unburned hydrocarbon emissions if you're off the sweet spot?
If you're, let's just say you're in, the sweet spot would be in the center and in between the CO and NOx limits. That's what we were calling the center or the ideal lambda. At that location, you are getting some hydrocarbon reduction and methane reduction. Probably, I don't have the numbers here handy, but probably closer to 50%. And so you are getting some methane reduction across the catalyst. And then as you move to the right on that curve, you do get more and more hydrocarbon reduction as you move lean. But when these controllers are set up, one of the big concerns is NOx because it's so nonlinear. And so most operators, when they set up the controls, are going to kind of skew towards the other direction to avoid that nonlinear NOx increase. But it really depends on the emissions limits and the person who's setting it up.
Gotcha. And then one other final quick question. When you showed lambda values, like in your presentation, was that directly from the UEGO sensor in the exhaust, or is that another laboratory measurement of lambda?
Those are directly from the UEGO lambda sensor in the exhaust. We did have multiple measurements of lambda, and we compared them. And, we ended up using the lambda sensors in the exhaust.
Okay. Yeah, just clarifying. So, okay. Thank you. Thanks, Dan. Really great job. I'll go back on mute.
Great. Really good questions. And I'm actually pretty shocked on my end. So I see there's a lot of questions. So, please be patient with us as we kind of work through the guests' questions. So I see that David Tikrobi has a question. So David, if you can, please unmute and ask your question, and then kindly unmute afterwards. Thank you. And if you're unable to find the unmute button, typically on the toolbar, it's on either the top right or the top left, and it's an icon with a microphone. You just simply press that. If it's green, then you have access to speech. Well, while David figures that out, I also see another guest, David Bleckman. He's also very interested to ask a question. So David Bleckman, can you please ask your question?
Yes, thank you. Professor Olson, I really appreciate your presentation. I'll be teaching engine design course in spring. Would like to invite you for a guest lecture to share your work with our students. I hope you would be open to that. And also a couple of things. One on hydrogen combustion. So you're doing a blend, but are there plans to transition to hydrogen, complete hydrogen on this engine, and with that, what it would entail, modifications on the engine for you to do this research? And also, I use in my classes, I don't know if you're familiar, Colorado State has modeling applets online, but it's getting harder and harder to use them as Java is being phased out. So this year I was not able to get them to run. They were running 2 years ago. So my just input, if there is a opportunity to update them to some modern way, because they're a really great tool to demonstrate engine thermodynamics and operations and all the details. So just all the feedback in one. But if you could comment on transitioning to full, 100% hydrogen.
Sure, I'll take the last question first. The applets, I also liked the applets, and those came with the combustion textbook written by Alan Kirkpatrick. And yes, those are being phased out. With the new textbook, he provides MATLAB programs that do the same thing. So the last time I taught IC engines, I used the MATLAB programs. So that's kind of where that sits. And certainly, if you have any other questions, you could email Dr. Kirkpatrick. The going to 100% hydrogen, a lot of this is driven by our research sponsors like SoCal. We don't have any plans or funding currently to go to 100% hydrogen on this engine. I think that we would definitely need to take a look at the fuel control valve. That's one thing. Will it flow the right amount of fuel if it were 100% hydrogen? As I mentioned, this research was really targeted at looking at up to 30% blends, and nothing is done to the engine. We just see how the engine responds. And one possible effect that we were concerned about, it didn't happen, but hydrogen requires a larger volumetric flow for the same power. And so we thought maybe the fuel control valve won't be large enough. I would expect to have to replace that if we go to 100% hydrogen. The other thing would be with regard to the backfires. We would definitely do something there. But in terms of our current research plans, we do have a new DOE project to develop a small hydrogen engine for a fuel cell engine hybrid application. But that's the only one that I can think of right now where we'll be dealing with 100% hydrogen.
Thank you so much. That was very interesting. Thank you.
Great, thank you. I just wanted to put in a self-plug for the SoCalGas RD&D program. So we're always looking for research partners to work with, and certainly we will be looking into possibility of funding the research, right? To understand exactly, what 100% hydrogen on engines would look like. So, certainly always looking for opportunities to help move the needle for our decarbonization goals. And then I see we have another guest interested asking a question, but I'd like to revisit David Tekrobi, see if he was able to kind of work out his technical issues to ask a question. If not, I'm going to move on to the next individual. Well, David, if you're not able to hop on mic, feel free to ask your question through the chat box and I'll be able to see it. So I'm going to hop over now to Matt Smith. Matt, if you're able to unmute yourself, go ahead and ask a question.
Hello, thanks, Dan. How are you doing? Yeah, I have a question on the application. Let's say you have a large compressor station. Where is the intended blend point? And if it's just on the fuel line, you're going to need virtual pipeline, truck trailer feed, for example, or I don't see where the infrastructure comes into play to use the blend.
Well, yeah. So I think what you're asking is how does the hydrogen get into the pipeline? If I'm understanding that correctly, and I think that's not really determined yet. But in our thinking, we kind of imagined, let's just say that you have the ideal scenario where you have wind turbines converting electricity to hydrogen through electrolysis. You have a buildup of hydrogen at that location. You locate that near a pipeline and you just inject it into the pipeline. And then the compressor station that's downstream of that would then need to run on a blend of hydrogen and natural gas. That's the scenario that we envisioned.
Okay, thank you. I just thought about the other effects of that would be the end user of the gas, and compressing that blend would have to be accounted for as well.
Exactly, and SoCal has other programs where they're looking at things like gas stoves, and certainly the compressors themselves. What's the impact of compressor efficiency if you have 30% hydrogen? So I think those type issues are being investigated by others. This was focused on engines.
Great, thanks again, appreciate it.
Great, thank you for the question. And I'll hop over to the next guest now. I see Psych Park is also interested in asking a question. So Psych, if you would like to ask a question, please unmute yourself so that you can ask that question. Thank you. Psych, are you able to unmute? If not, I'll oh, yes, Psych, we can hear you. Go ahead, please.
Okay, thank you for good presentation, Professor Urjan. I am newly joined in SoCalGas in hydrogen strategy groups. It's very informative presentation. When it comes to spark timing, I think we should compare exhaust performance by applying the optimal spark timing when the fuel change. What I mean is hydrogen blending cases. What do you think? What I mean, adjusting spark timing seems to control NOx more effectively. So I want to know what you say.
That's a really good point. So again, we were looking at the standard engine controller and, you know, nothing, not even an advanced controller. The LECM, for example, if combustion sensors are included in the engine, it can control peak pressure location or CA50. That's the crank angle for 50% heat release. So, so we were sort of evaluating what would happen in the case of a dumb controller. I'll put that in dumb controller. So absolutely, if we had employed more of a control strategy that is actively looking at the combustion process, it would have corrected the timing and it would have ignited later, and the peak pressures and CA50 would have been about the same, and we wouldn't have seen that increase in NOx. So, and also, I don't think we would have seen the narrowing of the control window. So I'm really glad you brought that up. So that's a really important point.
Okay, thank you, makes sense. And last quick question. As far as I know, it's a big power generation gas turbine plant. They want to use hydrogen to mix co-firing with hydrogen and natural gas. They use line mixer to make sure the mixedness is perfectly. However, can you ensure the mixing of fuel? What I mean is, did you install the line mixer or any other apparatus to enhance mixing hydrogen and natural gas?
Okay, so yeah, that's another good question. So we made sure that we had at least 10 diameters of mixing length between where the hydrogen came into the natural gas flow and the first component. So that would be kind of our first, you know, the first design parameter that we ensured. And then, you know, you're going through the fuel valve, the fuel control valve, and that provides some turbulence going into the intake air. And then you go through the turbocharger compressor. So we don't really, we're confident that the hydrogen and natural gas were well mixed by making those design decisions.
Okay, good. Thank you very much.
Great. I'm kind of excited for the next question, actually. So I'm going to go through the list of written questions, and I really like this question because I used to be an emission test engineer at the California Air Resource myself. So the question that this person's asking from Paul is this research applicable to the latest generation of automotive natural gas engines? If not, what sort of engine system modifications would be required for the engines to operate on hydrogen blended fuels?
Well, I would say, you know, it's applicable from the standpoint that automotive engines are stoichiometric engines and use a three-way catalyst. So, you know, I think that would be one thing I would say. However, you know, 100% hydrogen engine, I think it's going to be a lean burn engine. At least that's what I've seen in a lot of the literature. 100% hydrogen internal combustion engines operate lean. And so if you go back to that diagram of lambda versus emissions, rather than operating at stoichiometric and requiring a three-way catalyst, you're operating lean where NOx emissions are low and a catalyst is not needed. So I think, you know, it remains to be seen. It's very dependent on the engine configuration, you know, stoichiometric, lean burn, turbocharged, all these type of design decisions that go into the engine configuration.
Thank you. And some follow-up questions to that is, you know, did you find that there were any embrittlement issues identified? Was that ever studied? Any long-term impacts on the engine? Any thoughts on, you know, overall useful life? And then did you notice any impacts on fouling of the NSCR when the hydrogen was blended into the fuel?
Yeah, really, we didn't run long enough to assess either of those issues. And, you know, that's not the hydrogen embrittlement issue, I know is definitely of concern, but that's not really something that we're doing in my research group. And we just didn't run long enough to see any effects like that. Or on the catalyst, we did not see any catalyst degradation. Granted, we didn't run for very many hours, but we didn't see any catalyst degradation.
I see. Let me take 1 second to look through the list of questions, but really there's probably way too much. And most likely this might be the last question I ask today. Just to be respectful of everyone's time, I'm sure, you know, we all have really busy days and meetings throughout the day. So I think let's do this. Let's end the presentation today. And if any of our guests have any questions, guests can, again, reach out to the RD&D email address, and we'll kindly forward these questions to the appropriate experts within the company and outside the company, and we'll surely follow up. And again, I'm going to put on the slides for that contact information so that our guests can see, you know, all the different contacts that they can reach out to and resources for today's webinar. So one moment while I put that up. Great. So that contact information should be present now on the screen. And again, please feel free to reach out. We're actively, you know, looking for opportunities to partner up on research. But like I mentioned, it looks like we are just about time I wish we had more time for questions. I found this to be a great session for all of us. And again, thank you for your time and attention today. I hope that everyone found the presentation to be really good. And I hope that you have a very pleasant day. Thank you.